classes. So yeah, we're starting a new module today, module 4, which is about Bernoulli's equation. It's basically conservation of energy for a fluid, and it's probably one of the most important concepts in this class that you'll actually use it's quite commonly used in industry when we don't want to be doing things like CFD. So if you want to avoid the use of CFD, a lot of like analytical expressions in industry are based off of Bernoulli's equation or the concepts of conservation of energy in a fluid. So that's what we're going to cover in this section. So yeah, module 4 is going to be about Bernoulli's equation and its extension to internal flows. Here's the topics we're going to cover. So today we're going to talk about what Bernoulli's equation actually is. Then we're going to go through basically different types of pressures that we can measure using Bernoulli's equation and how Bernoulli's equation can be used to measure pressure. We're going to talk about how we extend. So the end of this topic is basically what you need for your project. And that involves these internal flow concepts like different losses. How do we know how much pressure we need to provide with a pump or a fan to push fluid through an internal system? So as you can imagine, that is quite a widely applicable outcome of this extended Bernoulli's equation. So our learning objectives for today are we're going to derive Bernoulli's equation under certain assumptions. We're going to list those assumptions. So Bernoulli's equation is all about the assumptions. It's a really simple equation, but it applies for very restrictive assumptions. So we're going to clearly list those. I'm going to discuss Bernoulli's equation as an interpretation of conservation of energy for a fluid. And we're going to do some simple examples with Bernoulli's flow. So predict fluid flow using Bernoulli's equation. Okay, so let's go right on. Okay, so the first step we're going to do is the derivation. So let's consider steady flow along a streamline. I'm going to underline some important stuff that we're going to do throughout this derivation in green, and we'll collect that at the end. So we're going to consider steady state flow along a streamline. These are concepts we've seen so far in this class, so hopefully you get familiarity of what that means. So we're going to be working along a streamline when it comes to Bernoulli's equation. Okay, so we're going to take, say we have some streamline in our flow like that. We consider sort of a fluid parcel moving along this streamline there. Actually, I'm going to define this. I'm going to define the fluid parcel at sort of an angle so we can see the coordinate system here. So let's look at the fluid parcel at this part of the streamline. We're going to define a coordinate system based on the streamline so the red is our coordinate system there. So we have an S hat coordinate vector and an N hat coordinate vector. So the S hat coordinate vector is always tangential to the streamline. And so we know now that means that it's tangential to the local velocity vector all along the streamline. So for example, at this point down here, the coordinate system is defined so that it's always S hat, N hat, where those are always along the streamline. Let's compute the material derivative, the acceleration of this fluid parcel as it moves along the streamline. So acceleration is dv by dt. We looked at that in the previous module. So the first term of our material derivative is partial v by partial t. The second term is v partial v by partial s. So this is the acceleration along a streamline. So this partial s, that's partial s. Before we saw it was like partial x or partial y, partial z. So in general, remember, that's just the spatial acceleration, and v is the rate that we move through space. So this term here tells us the Lagrangian perspective of our fluid parcel as it moves along this streamline, how the acceleration changes. So since I mentioned we're dealing with a steady flow, this first term will go away. And so we have A equals, now we can also simplify this spatial rate of change term. So right now, acceleration is a vector and velocity is a vector. But what do we know about the relationship of the velocity vector and our streamline coordinate system? Okay. Yes, exactly. Our velocity vector is always tangent to the s direction. So we can simplify this to just v partial v by partial s. So this is the acceleration in the s direction, s hat direction. That's because the definition of a streamline is that our velocity v, so, depends on the coordinate system, we can say it's vx I hat plus vy j hat. In our coordinate system here, our velocity is 0 n hat plus some velocity v s hat. I'm going to write those in red just to be clear. So we've defined our coordinate system in an extremely convenient way here, that we basically only have velocity along we only have velocity along one direction of our coordinate system. Are there any questions about this coordinate system thing here? So we've done A, but let's consider F equals ma in the s hat direction now. So we know that F equals ma gives us in this course, we're using the incompressible Navier-Stokes equation. And we're also going to drop one of the terms right off the bat. So we're going to neglect viscosity. You know how when you're first learning physics, you don't do anything to deal with friction when it comes to energy, conservation of energy? That's the equivalent here. So for certain flows and in certain cases in flow, even like certain parts of certain flows, you can basically neglect viscous effects. So that's what we're going to do here. In general, you can't do this, but we're going to do that in this derivation. So neglecting viscosity gives us something called inviscid flow. And inviscid is just a fancy word for no viscosity. Okay, so the incompressible Navier-Stokes equations without the viscosity term are rho dv by dt negative nabla p plus rho g. So again, there's no viscous term there. And we're going to look along the s direction. So we did rho v partial v by partial s equals negative partial p by partial s minus rho. This is how we're going to define the gs. Minus rho gs. I'll talk about that rho gs term in a sec here. Let me just take a step back. So we started at the incompressible Navier-Stokes equation. It's a vector equation. It doesn't care what coordinate frame you're in, so it has multiple components. In our coordinate frame, we have n hat and s hat, and we're looking at the s hat component of the incompressible Navier-Stokes equation. We get this. So that nabla p term, nabla p, the gradient of a scalar field produces a vector field, and the s hat component of that is partial p partial s. Okay. So I'm going to talk about the gs here. Let's assume our gravity vector is just down. And these are our, so say we say G equals negative G J hat using, say, an I hat J hat coordinate system. So the coordinate system is just y is defined upwards, so our gravity vector is downwards, so G is negative G J hat. So in our tangential normal coordinate system, that will have two components now. We'll have some GT T hat plus GS S hat. Okay. Now there's an angle here, theta. We can compute GS is negative G sine theta. So, and just as a reminder, our S hat in this would be like this, and our N hat would be like that. So that's our, these two things are two different coordinate frames. And we're used to gravity being downwards, and our tangential normal coordinate system is always tangential. So this is at one particular angle. Yeah, lots of questions. Ian, maybe?
Yeah, so why are you using T hat instead of N hat?
My bad. Yeah, that should be N hat. So, yeah, so let's do G N hat. Okay. So N hat. Right. Okay. Yep.
Um, do you, is it kind of arbitrary which direction you do like S hat for like the dotted line for positive?
Um, yeah, in this case, it's negative because the way we've defined theta there,
Right.
it would be opposite S hat. Aaron, did that answer your question? Same question? Okay. I'll be honest, like don't worry too much about the signs and little things like that in this derivation because it's the last time you'll basically see it. Um, the what we're gonna do now is replace that sine theta using our coordinate system rotation, and then put that back into our F equals ma. Okay, so let's do our, say we have some ds there. Okay, so there's ds there. Dx, horizontal. We're going to call the vertical dz. So this j hat should probably be k hat, just to be strict. So we're going to call the vertical k hat. It doesn't matter. This is just because the convention for Bernoulli's equation is to call height z and not y. Okay, so then the theta angle will be here. This tells us that sine theta is dz over ds based on the geometry. I apologize if I confuse anyone with the coordinate system there, mixing up y and z. It doesn't really matter in this derivation what variable you call the vertical direction. What we're trying to do here is just convert our normal gravity, which we know is downward, into some sort of expression that we can always use to calculate the s component of that gravity for our force balance. So are there any questions about that? We haven't made any assumptions here regarding the gravity other than it's downward, but that's not even considered like one that you need to list. So you can just assume gravity is downward. Okay, so we now have rho v partial v by partial s negative partial p by partial s minus rho g dz by ds. So Again, this is the S hat component. So rho gs is rho g dz ds, where z is our vertical coordinate and ds is our tangential coordinate. So we have two different kind of coordinate frames, variables coming from two different coordinate frames being expressed in this equation, which is interesting. Okay. So we can just do some rearranging and some math here, so we can cancel our ds's. So that gives us rho v dv is negative partial p minus rho g dz. So we start to see, yeah, Mikey.
Sorry, I missed it. Why does S equals D Z ds?
So that's, maybe it's not clear. This is g sub s.
Oh.
Yeah. So the question was, why does s dz ds? But that's just g sub s. So this is the s component. So that would be this gs here. That's this gs. Okay. Yep. Aaron? Yeah. G. Yeah, yeah, yeah. Yeah, I can correct that. Yeah. So the point I want to make is we start seeing like basically what a differential equation like this tells us is d is a small change. So this tells us that a small change in velocity multiplied by the velocity and density equals the small change in pressure minus a small change in height. So this is where our energy balance starts to come out. So we're basically going to have, these are going to end up being three different terms in an energy balance for a fluid along a streamline. There's going to be some sort of kinetic energy measured by the velocity. There's going to be some sort of like pressure energy, which is like a potential energy. Then there's going to be some sort of vertical gravitational potential energy. So I'll make that change there. Thank you for pointing that out. Okay, so GS will be, so that should basically be plus here, right? Okay. Okay. So for steady state flow along a streamline, we have, yep.
Partial b at the beginning become a dv in the next line.
The partial p, this is still a partial p here. Yeah.
No, the first.
The first term?
Yeah, the
Rho v dv. Oh, yeah, yeah, okay. Okay, so that's still partial b. Yeah, so I'm going to talk about now how we can basically convert those partials into just regular derivatives. So we're considering kind of flow along a streamline. We only have one coordinate that defines that, and that's s. That's along our streamline. We also have steady state flow. So what this means is that for steady state flow, along a streamline, our velocity is only a function of our coordinate along that streamline, s. So we're going to restrict ourselves to just traveling along a streamline. So what we've actually done is taken a 2D, say, flow field with streamlines running through it, and we're looking at like a 1D subset of that flow field. So we're considering a line through that flow, and that line is a streamline. So it's a special line through that flow, and now we kind of have a 1D point of view. So V is V of S. Same thing with pressure. Pressure is a function only of S, where S is the coordinate along a streamline. So along a streamline, I'll say that, I don't know how many times I'm going to say that this lecture, but along a streamline is like a really important and I would say heavily abused assumption of Bernoulli's equation. So along a streamline, period. So what we get with this now is we know that partial V by partial S is actually just dV by ds, because V is only a function of a similar variable. Same thing with partial P by partial S is just dp by ds. So maybe I canceled these partial s's too soon here. Okay, so we have rho v dv by ds is negative dp by ds minus rho g dz by ds. So now the reason I said I canceled them earlier was because I was kind of canceling like partial s with ds, which I shouldn't do. ds only cancels the ds. So now these are all ds's because we've restricted ourselves to a 1D line through our flow field. So these s's can cancel out now. We get the equation that I wrote earlier, but in terms of d. So rho v dv negative dp minus rho g dz. Okay. So I'm going to collect everything on one side and then integrate this. So the integral looks like integral of dp plus integral of rho v dv plus the integral of rho g dz equals 0. So just move everything to the left-hand side and integrate both sides. So technically you need to integrate 0. What's the integral of dp? It's not a trick question, just p. Yeah. What about rho v dv? Rho v squared over 2, I think I heard. Okay. Rho v squared over 2. What about rho g dz? Assuming that rho and g are both constant with z, which is rho gz, right? Rho gz. What about the integral of 0? It's a constant. Yeah. I heard both 0 and a constant, but the integral of 0 is a constant. The other way you can think about this is we just collect all the constants from these indefinite integrals on the left-hand side and put it on the right-hand side. So this is just a constant. So what we've done is we've integrated a bunch of forces along a streamline under certain assumptions. And we've got a sum of a bunch of different terms that are a constant always along this streamline. So I'm not sure if you've seen like work and energy derived that way, but this is the exact same thing that's done in like normal to derive the conservation of energy in terms of like the kinetic energy of a ball and the height of the ball and things like that. All you do is when you integrate conservation of momentum, you get conservation of energy. So that's what we've done here. We started with conservation of momentum and we integrated this along a path. If you go back and look at your notes, you might not have understood it at the time, but maybe you might have more understanding now. If you go back and look at your kinematics and energy notes, that's basically how you derive like the 1/2 mv squared plus, I guess, my or whatever equals constant. Mgy is constant. So this is basically energy is constant. So total energy is constant along streamline. So I'm going to talk a lot about the implications of this equation now and what we can do with it. But are there any questions so far? No? Okay. So what this means is that since this is constant, if you pick 2 points along a streamline, say you have some streamline here in your flow, and we pick a point here, call it point 1. we pick a point here. We'll call it point 2. Energy is conserved between those 2 points. So we're talking about steady state flow. That means a streamline is a path line, right? So a streamline is actually the path the fluid parcels are going to travel. So you can think of this as the fluid parcel is going to be at 1. It's going to go through, the energy is going to convert between different types, but the total energy will be conserved when it arrives at point 2. So this means that P1 plus rho V1 squared over 2 plus rho G Z1 is P2 plus rho V2 squared over 2 plus rho G Z2. Now, so this is like a more common way to state Bernoulli's equation. So I want to just talk a little bit about the definition of Z. So it turns out that as long as Z1 and Z2 are measured from the same datum, again, this is the exact same thing for like potential energy when you're doing like more, I guess, conventional conservation energy. The actual point that you measure these from doesn't matter. So we can say that that's Z1 and that is Z2. As long as both 1 and 2 are measured from the same datum, this equation will give the same results. It's about the difference in height between those 2 points. This is also the same. It's probably more common to say, if you know these variables at point 1, why not just set, say, Z1 equals 0? That means that Z2 will be this height. So using, say, the orange definition. Whatever way you define it, it doesn't matter. The results are still the same. Okay. Any questions about this? No? Okay. So I'm going to define these different terms in here in this conservation of energy equation. So conservation of energy which is loosely the integral of F equals ma. So our fluid has 3 types of energy, which we can see in this. So we have rho v squared over 2. That's kinetic energy. We have rho gz. That's gravitational potential energy. We have P. So we might have an additional term in here than you're used to seeing in conservation energy. Like maybe a more traditional one is just converting between kinetic and gravitational potential energy. But you can think of P as like an additional source of potential energy that the flow can carry with it. So it's like if your like point mass as it's converting, say like when you like launch your point mass and you're trying to compute the maximum height, if your point mass can somehow like power itself, that's kind of what P is. It's like an additional way to draw kinetic energy. So P is going to be called, yeah, so you have a question?
If you compress, like if you add pressure to an incompressible, if you add pressure to an incompressible fluid like water, are you doing work?
That's a very good question. So in terms of energy, we'll see that the answer is yes, but it's the pressure increase that you get by compressing water is takes a lot of work to do. So it's not something that we'll do. Also, this equation doesn't consider any external sources of work. So that's one of the assumptions we'll talk about at the end of this. But it's a very good question. Yeah, because how can you do work if there's no distance? But it's a ds. So yeah, good question though. Okay, so P is like it's called flow energy, but I'll call it flow potential energy. And the total energy is conserved. Any other questions about this? So I'm going to start doing examples now where I talk about like situations where we could use Bernoulli's equation, and we'll get more of a feel for how we use this. But are there any questions about um, these different types of energy in a fluid? No? So we're going to do an example now. It's going to be a little bit interactive. So the goal of this example is compute the maximum pressure that could be exerted on the plate. So we want to compute the maximum pressure. So let's say we have some plate here. It's going to be like a wall or a plate. Let's say we have some flow coming in with these conditions. So at 5 meters per second, atmospheric pressure, and it's air, so we can say 1.2 kilograms per meters cubed. So what this air is going to do, this is just straight up air blowing on a plate, okay? So it's going to hit the plate, sort of go up. I think you might have seen this streamlines later on. So I'll kind of set you up to solve this problem, but I'll ask you to solve it on your own. So let's assume we have a streamline here like this. So 0.1 on that streamline is going to be there, and 0.2 is going to be the point at the wall where the fluid slows down completely. So, okay. So energy is conserved along this line. So if I tell you that there's a streamline that actually does this, that starts out in the free stream with those properties and goes to the wall and completely stops, now we can actually compute the pressure that's on this plate. So the equation is P1 plus 1/2 rho V1 squared plus rho G Z1. P2 is 1/2 rho V2 squared plus rho G Z2. So that's the general conservation of energy equation. So as kind of a understanding check, what I'm going to have you guys do is compute this maximum pressure that could be exerted on the plate yourselves, and then we're going to submit our answers through Menti, okay? So you can start now if you've got this copied down, but copy this down if you haven't yet, and then we're going to submit our answers. So here's how we solve this problem. Okay, let me just get your attention again. So I'm just going to explain how we solve this problem. Okay, so let's say Z1 equals Z2. So we say they're at the same height. I'm going to solve this in gauge pressure units. So I'm going to say P1 equals 0 in gauge pressure. I'm also going to say V2 equals 0. So I'm going to assume the fluid completely stops at the plate, and that means that all of the flow potential, all the flow kinetic energy out in the free stream has been converted into pressure potential energy at the plate. So if V2 is non-zero, some of that energy is still remaining as kinetic energy in the fluid. So that just gives us P2 is 1/2 rho V1 squared, which is 1/2 times 1.2 times 5 squared, which is 15 pascals. And again, I'm working in gauge pressure units. So are there any questions about this example after having worked through it? Okay. Let's do a second one. It's going to be the same format, okay? So the question is a pinhole leak occurs in a water tank. What is the maximum velocity of the spray? So assume you have this big tank of water and there's a very small leak that occurs. The water is going to start spraying out of that hole. So we're going to determine now what the maximum velocity of that spray is. So rho is 1,000. I take G is 9.81. So we're going to have some tank of water. Let's say this leak occurs at a depth of 5 meters in the fluid. So again, we're going to use this equation above. P1 plus 1/2 rho V1 squared plus rho G Z1 is P2 is 1/2 2 squared G Z2. So there are actually two ways to solve this problem and get the same result. So I think if I asked you guys to solve this right now, some of you will do it one way and some of you will do it the other way. But you do get the exact same result. Okay, so I'll ask you to solve this problem now. But we only have a couple of minutes, so solve it quickly, please.